sorry, picking up where I left off. If you multiply these, there's 3 ways to do this. Then you get 0.4096. Okay. If we change it and do it without replacement, then we still have 3 ways of doing this. But what happens is the first card, if I get 12 out of 52, so it's a face card. The next one I pull out, I don't want it to be a face card, so I still have 40, but how many cards do I have in the deck now? If I left one out, it's 51. And now if I don't want another face card, I want a regular card, I've already left one out, so now I have 39 out of 50. Okay, so when you calculate this, you get 0.423, so you're slightly higher probability of actually having that happen when you leave cards out of the deck. Okay. All right, so here are some vocab for this chapter. So sample space is a random phenomenon, is the set of all possible outcomes. An event is any outcome or a set of outcomes of a random phenomenon. An event is a subset of the sample space. Okay, so it's part of the sample space. The probability model is a mathematical description of a random phenomenon consisting of 2 parts, a sample space, S, it's a capital S, and a way of assigning probabilities to events. Okay, there's 2 types of probability. Empirical probability is the probability based on actual observation. And theoretical probability is probability based on what should happen. Okay, so like when you toss a coin, well, if you toss it 2 times, you may not get a head and a tail. You might have, 2 heads. But over time, what's going to happen in the long run, if you actually observe your actual observation, it will turn out to be the probability of getting the head is 1/2. Okay. All right, flipping the page. A tree diagram is very helpful. It begins with a point and you draw a line from each possible outcome. Additional lines are drawn to each new outcome and so on. The result looks like a tree branch. An outcome in the sample space is one of the paths through the tree. Okay, so list a sample space when flipping a coin 3 times. So we're going to do this just listing it, and then we're going to do it also drawing a tree diagram. And you'll see why sometimes it's really helpful. Okay, so our sample space is a capital S. We're going to use a set notation. We're going to list all the possible outcomes when flipping a coin. So we're just going to try to draw this out using like a pattern. So here I'm going to start with tails, tails, tails. And then we can have a tail, tail, and a head. But then it can be in any order. So I'm going to move that head from being last to middle to first. Okay, then we could have 1 tail and 2 heads. But again, that could be in any order. And the last thing is 3 heads. Okay, so that's our set notation. So how many different outcomes were there? Sometimes it's helpful to know ahead of time. This one wasn't very large, but once you start getting to like flipping a coin 4 times, there's quite a lot of options. So how many options do we have on the first flip? We had a head or a tail, so there were 2 options. Same with the second and same with the third. So this is actually 2 to the third, which is 8. So as soon as you start to get to flipping 4 or 5 coins, you're talking about quite a lot of outcomes. So it's usually nice to have the total before you start mapping them out. Okay, so what a tree diagram looks like is on our first go round, we either could have a head or a tail. Then we're going to flip the coin again, so we could either have a head or a tail, or a head or a tail. And then we're going to flip it one more time, and so then we get a head or a tail, a head or a tail, a head or a tail, a head or a tail. Okay, and one of the paths, one of the outcomes is the whole path down the branch. So this is just what the tree diagram looks like. But notice how on the sample, when we listed out the sample space, an outcome was like a head, head, tail. So you would need to follow the whole branch. So here you get a head, head, and a tail. That is one outcome, following the branch all the way down. Okay, so that's how you would write out the outcomes. All right, so some probability rules. Some of these you may have seen before when you've done probability in your other math chapters, but we're going to go over some. Okay. Let A and B denote two events. The event not A consists of all experimental outcomes that are not in event A. It's also known as the complement of A, so you'll see that. And it's usually denoted by a complement, so it's like a C in the superscript, or you'll see a prime with just like a little line there. Okay, the complement rule states that the probability of A complement is just 1 minus the probability of A. Probability of A has to be between 0 and 1. Probabilities are all between 0 and 1. The event A or B consists of experimental outcomes in at least one of the two events. It could be in A, it could be in B, or it could be in both. A or B is known as the union. Okay, and it's denoted, like in set notation, is A union B. Okay, so you do need to know these notations. So that's for your or. Okay, it's a union. The event A and B consists of all experimental units that are in both of the events, A and B. Okay, they have to be in both. A and B is known as the intersection of the two events and is denoted as A intersect B. So it's like an upside down U. Mutually exclusive or disjoint. You'll see both of those words. They mean the same thing. They are events that have no outcomes in common. And then if two events are disjoint, then A or B equals A plus B. And the sum of probabilities of all possible outcomes in the sample space must equal 1. Okay, so the sample space is the total thing. All right, so we're going to draw some Venn diagrams. I'm sure you've seen these. These are like the circles that intersect. Okay, that's what we're going to talk about. So the union, what we look at is, if I draw sort of a circle, event A and B. If we look at A or B, which is the union, it's also called the or. Okay, so it could be in A, it could be in both, and it could be in B. Anything in there. The next one we're going to draw is the intersection. Okay, it's where the two events intersect. Okay, so A and B. So when we look at our two events, A and B, it's really just where they overlap, where they intersect. Okay, so this little part in here, where A and B both happen. Disjoint, or it's also called mutually exclusive, is when two events have no events in common. Okay, so your A and your B have no overlap. All right, so we're going to use a Venn diagram to solve this particular problem. We're going to kind of look at multiple ways to solve this type of problem. So later in the chapter, we'll look at another way to solve this, but this is how we're going to solve it now. So we have randomly selected 100 juniors enrolled in pre-calculus at Oak Ridge High School. 55 of these students are taking AP Calculus AB next year. 35 are going to take AP Statistics. Of those, 10 are going to take both AB Calculus and AP Statistics. Okay, so we're going to construct a Venn diagram here. So we've got, they're either taking AP Calc, or they plan on taking AP Stat. Okay, so I like to write the totals on the outsides. Okay, so AP Calculus, there's 55 total. For AP Stat, there is 35 total. Okay, those are our total numbers. How many are taking both? Okay, we're going to be 10. Oops. Oh, I erased a lot more than I thought. Okay, sorry. Oh, that's not really a very good circle. All right, so 10 are taking both. Okay, so that's where that 10 comes from. So this total sort of circle here is supposed to add up to 55. So if we already have 10 taking both, there would be 45 then who are just taking calculus and not taking both. Okay, for statistics, then there's 25 who are just taking statistics and not taking both. All right, to answer the questions now for B, what is the probability that a randomly selected student enrolls in both AP Calculus and AP Statistics? So probability that they take Calc and Stats. Okay, so that notation, set notation is important. It's an and. Okay, so we know there's 10. Out of how many juniors is this totally out of? Well, they selected 100 juniors and sampled, so we get it out of 100. So this is 0.1. Okay, what is the probability that a randomly selected student enrolls in only AP Calculus? So really how we're going to write this, because we have two events here. So this is calculus and not AP Statistics. So we're going to write an and, stats, and then complement. So this is calc and not statistics is really what this notation is saying. Okay. So where in the Venn diagram, we do not need to do any calculations to find this number. Okay. Note to self here, do not multiply. This is what so many people want to do. Do not multiply probabilities here. Note to self, look at this problem. This comes up all the time. Okay. We just look in the Venn diagram. Look at the diagram. That's why we drew it. Okay, can you tell this happens a lot? Where in the diagram did they take calculus and not AP Statistics? Can we see it? It is this area over here. This is the students who are taking just calculus, not both, and not AP Statistics. So there are 45 out of our total of 100. Okay, 0.45. Note to self, don't be the one, don't be the student who multiplies. Don't do that. It's not good. Okay, switching the page. All right, question D. What's the probability that a randomly selected student does not enroll in AP Calculus? Okay, so probability, calculus, complement. So not calculus. Could they have enrolled in statistics? Yes. Could they have enrolled in neither of these classes? Yes. So it's everything outside, just the circle for calculus. So we're going to do 1 minus how many students were in calculus all together. That whole circle is 55 out of 100. Okay, so that gives me 0.45. All right, and then what is the probability that a randomly selected student does not enroll in either AP Calculus or AP Statistics? Okay, so when we look at, I'm just going to sketch our Venn diagram here for Calc and Stats. They did not enroll in calculus or statistics or both. So it's basically like we have events outside of here that, you know, people who didn't take either of these classes are taking something else. So we have everything outside of this Venn diagram. So what we want to write in probability notation is the probability of calc or statistics complement. Okay, so this is the or, stats or statistics, and it's not in there, so it's the complement. Okay, so we're going to do 1 minus what's in this Venn diagram. These three pieces. We had 45 here, 10, and 25. So it's 1 minus the 45 plus the 10 plus the 25 out of 100. Okay, so there's 80 students there. If you could just calculate that. So this is going to be 0.2. There's 20% of the students who do not take calculus or statistics. Okay. All right, example 9. Customers at a certain store pay for purchases with either cash or one of 4 types of credit cards. Store records kept for a long period of time indicate the following probabilities of type of payment. What is the probability that the purchase is made with a nationally distributed credit card, MasterCard, Visa, or American Express? So here we're assuming that they only pay one way. They're not splitting their charge multiple ways, okay? So they're only paying with one card. So can you tell if they only pay with one card, these events are disjoint. They're only paying with cash. They're only paying with the store credit card. They're only paying with MasterCard. This is an example where these are disjoint. If you drew a Venn diagram, they would just be like separate circles. The probability that they pay with this way, this way, this way, or this way. Okay? This is an example of this. Okay, so nationally distributed credit card, what's the probability they pay with a MasterCard or, so Union, Visa, or American Express? Well, since there's no overlap, we can just add them. 0.18, 0.15, and 0.12. Okay, so that is 0.45. What is the probability that a purchase is not made with a nationally distributed credit card? Okay, so not one of these. There's 2 ways you can solve this. You can either sum up the other probabilities that are not included in this section, or, to write it out, probability that's not MasterCard or Visa or American Express. That, in this case, is just 1 minus the probability of MasterCard, Visa, or American Express. Sorry, my U and my V are looking very the same. That's for Visa. Since we already found that probability, we're just going to do 1 minus 0.45. That's what that answer is. Okay, so 0.55. All right, example 10. If digits are distributed at random among the digits 1 through 9, then each is equally likely. The sample space for single digits is 1 through 9. Okay. What is the probability of each number being selected? Well, the probability is just 1 out of 9. Okay. Leaving things as fractions is perfectly fine, like this. You don't have to write it as a decimal. Okay, unless you're doing a calculation, then go ahead and solve it, but fractions are good. All right, what's the probability that a digit, the first digit, so any digit, is greater than 6? Okay, so greater than 6, how many are there? There's 3 of the 9, which is 1/3, or 0.33. Okay. What is the probability that the first digit is at most 3? Okay, so does at most 3 include 3? Yes, it does. It's less than or equal to 3. So here again we have 3, 1, 2, and 3. So this is 1/3. What's the probability that the first digit is at least 8? Oops. Okay, that it just includes 8 or 9. So we've got 2 out of 9. What's the probability that the first digit is not divisible by 4? Okay, when we look at our numbers, which ones are divisible by 4? Let's see if we can go there first. Okay, so 4 is obviously divisible by 4. What's the other number that's divisible by 4 in this set? It's going to be 8. Okay, so of those numbers, what's the probability that it's not a 4 or an 8? Well, there's 7 other numbers out of 9. Okay, so those were some of our general probability rules. And then we're going to talk more about conditional probability in class. Thanks!